Yes, sir.
Okay, sure. Thanks, Karthik. Yeah. Good evening, everyone. I think we have 3 students who joined: Harith, Vivek, and Goel.
Good evening.
Good evening. Good evening. I think. So, is there also a YouTube link that we should be checking?
Just your shared unit chat.
But I think the Zoom link is also provided, right?
Yes, sir. Yes, sir. Both, yeah. Zoom link and also YouTube link.
But then, so I guess anybody who wants to interact may, like, I don't think I'll have to track the YouTube comments.
No need, sir. Just you can go with that. Yeah.
That we should be checking. Okay, I'll just open it anyway, in case there are somebody who chat there. But then they can always join the Zoom, I suppose. Okay, so maybe we'll start. We'll start. Sure. So maybe what I'll do is there is a set of questions that was shared with me. I'll just go over it, and then let us and then if there are other things that you want to ask, we can discuss that. So I think Vivek is the first one who. There are 2 questions that Vivek has asked. All of these questions, so I'm just reading out your question, Vivek, pertain to start doing publishable quality research in computational complexity. And the questions are, could you please suggest classic papers in computational complexity and quantum computational complexity that can be read on the completion of this course? Could you please read and work out a paper in computational complexity in front of the future live sessions, sort of a paper reading sessions? And could you please help focus the art of coming up with solvable problems and publishing in computational complexity theory? I think, see, number 1 is, can I suggest some papers? Sure, I could look at it. I've not looked at it prior to this meeting, but I could suggest maybe a couple of papers for you to read. But then my first point is, how familiar are you with computational complexity theory? If you're not familiar, the first step is actually to do this course or do a course in computational complexity or understand what is computational complexity before thinking about publishable quality research. So first, my suggestion is to complete this course, or basically the material that we are doing it. So either through this course or through some other course or by self-learning, one has to complete. At least maybe the 60-70%, the first 60-70% of this course one should do. Maybe the week up to week 10 perhaps, right? So, but I can of course suggest some papers, but that is not really within the scope of this course, like suggesting a paper to read, etc. But I can if you email me, I could suggest some things. You can find my email from my website and then send me an email. And read and work out a paper in computational complexity in one of the live sessions. I'm afraid it may not be a very practical thing to do. So so first of all, read and understand a paper is something that may take a long time. It may not be something that like doing a couple of problems in the live session. It may be not something that's as straightforward as that. It may be because sometimes you read, there are so many aspects to understand the paper. Sometimes it takes me days of sustained reading to complete days of sustained reading to complete reading the paper, and sometimes even more days to like just sit and thinking about it to understand the paper. So it is not something that I could do at a half an hour or 1 hour live session, right? It's because usually the papers in this area, it require a lot of thinking and a lot of abstract understanding. So it is not something that we could do in one session. It's something that, like, usually when we advise PhD students, it's something that happens over something that happens over a period of time. Like it's not like something in over one session you read a paper. That's almost always not the case, right? So it's not something that we could do that. Solvable problems and publishing in computational complexity, that's also something that is not so easy. It's something that cannot be taught or told over 5 minutes or 10 minutes, right? So it requires, so you're asking how to do research in an area, right? So people usually do, so I think you perhaps you are a PhD student, so people usually do PhDs, and in the process of the PhD, one of the expectations is that we train a student to be capable of doing exactly this, right? Coming up with understanding science, understanding some phenomenon. So in the area of computational complexity, you are trying to understand the area of computational complexity better, right? So there may be aspects that you are curious about, and one has to ask questions. Some questions may be easy, some questions may be immediate, some questions may be already known, some questions maybe the answer is opposite of what you think, some questions the answer is unknown, and in that process you try to find out the answer to that, and in that process you discover more about this field. This is what happens in any field, and that's also what happens in computational complexity. So it is, again, this is not something that I could teach in a live session. It's something that happens over a period of time. It can only, one gets to know this. Like I don't claim to be an expert at this myself, right? And it's just about asking the right questions and keep persisting on it, right? So you're in a way you're asking how to do research, or how to complete how to progress in your PhD. That's what you're asking. So there is no like one word answer. It's like a sustained effort over a period of time. One has to keep trying various things, various angles, and keep working on it, working at it without giving up, right? So there is no, I don't think there is any easy shortcuts or anything of the sort for this, right? Yeah, that's all I have to say about that. So Vivek, you are here, so you want to
Yes,
ask
sir.
something? Yeah, you can ask.
Yes, sir. Maybe, sir, I'll come back again on this.
Yeah, so I'm happy to discuss, but then it's not something that I could tell in a like 5 minutes or 10 minutes. It's a huge thing that you're asking, right? It's a
I understand, sir.
one. So are you a PhD student yourself?
Yes, sir.
Okay, in which institution?
NIT Patna, sir.
So in some sense, the PhD is supposed to train you for this, right? So this is something that one learns over a period of time. Again, PhD may not make one perfect, but still one continues to learn and one continues to get better at these things. Right?
Yes, sir. Yes.
So my only one advice is to be persistent. Don't give up. Keep working at it. Ask the right questions. Like if you find something. So, but that you have the basics kind of like you are from the questions. The basics is like you read more, you understand more, and you keep asking the right questions and trying to figure out the answers. I think that is the process. And by one way or the other, one will figure out how to like you may get answers in some cases, you may not be successful in some other cases, but then that's how research is. Not like you see some professor publishing papers, or you see some other student publishing papers, they may have tried 10 things, maybe they may be getting papers out of 2 of them, right? So there is a lot of failures that one does not see, right?
Yes, sir.
Yeah, that's one point. The next next question is from Harit. 2 questions. What is algebraic complexity theory? Can we, and number 2 is, what can we do computational analysis over FA model? Why do we choose to do a complexity analysis over TM model? So I'll answer them in this order itself. So what is algebraic complexity theory? Algebraic complexity theory is an area, sub area of complexity theory which tries to understand algebraic computations. So, so basically, most of complexity theory was like evolved over from like maybe starting from 70s in an attempt to answer the P versus NP question. Algebraic complexity theory also, one could say, was one of the attempts, right? So basically, you have algebraic objects like you have these fields, groups, etc., rings, etc., and then you can have polynomials. How do you make computations? So you can do computations over polynomials. You can try to understand, like, for instance, we will come across something called polynomial identity testing during the course, right? So given a polynomial, how do you tell whether it's a zero polynomial? So it may seem like a trivial question, or maybe it may seem like a trivial question, but sometimes it's even that is not easy. So for instance, I give you two polynomials, f and g, and you can only ask questions like, and these polynomials are not given to you in the usual polynomial form. Instead, you have black boxes, meaning you can ask what is f at x is equal to 5, and what is g at x is equal to 5, and then you get some answer. So now, is f equal to g? Like, are they the same polynomial? How will you answer that? So you can ask questions about polynomials. You can ask computational questions about polynomials. Another example is determinants. Is like an object, an algebraic object which is defined over matrices. So there are such algebraic objects, and one could define, or one could ask questions about these algebraic objects. One could ask computational questions about this. So algebraic complexity theory is a sub area that deals with this, right? So like many other sub areas, this also came about by trying to, in an attempt to answer the P versus NP question. Right. So there may be, I could share some notes or some other reference material if you're interested. I think there are some workshops or some events that have happened where people purely looked at this. There are also, I think, there may be, I don't know, I have to search, but there may be courses. There may be courses that have been taught on this topic. So yeah, if you're interested more, I could share something.
Sir, am I audible?
Yes, you are audible.
Yeah, okay. Okay, so where do you use like the rings and okay, rings is polynomial rings will be using fine. Groups and all, like, is there an explicit way of using, or is there any other algebra thing that we will be using apart from polynomials?
So where do you use as in, I was just giving an example. So, but polynomials is something that is well studied in algebraic complexity. Another thing is arithmetic circuits. We will see later in this course.
Right.
Right. So this is another example of algebraic objects.
I also like the example that you said that two polynomials f and g. So we are saying that f we want to check when f is equal to g, right?
Correct.
So
this
that means
this is known as the polynomial identity testing problem. Like, how would you check whether f and g are the same?
If f minus g is 0, identically
correct.
0.
Then how do you check whether something is 0?
For every input we given, that must evaluate to 0.
Yes, and it's like not just that, it must be. So we want to know whether it's a zero polynomial. So zero polynomial is not the same as over some inputs it evaluates to 0. Like, we want it to be the zero polynomial itself.
Right. Okay.
So how do you check that? So this is one of the is a very important problem in complexity theory, but this is, one could say, is an algebraic complexity question.
Okay.
So there is also this question. There is also this complexity classes called VP and VNP. Some people say that these are algebraic analogs of P versus NP, and people have tried to look at this, like VP versus VNP as well.
Okay. Is it known like L and NL? Like, it is not known like L and NL. L. Sorry. Yeah. Okay.
No, I didn't understand. So these are different complexity classes, not something that I've defined or not even in the course. I don't get into algebraic complexity theory in the course,
Oh,
not
okay.
explicitly, but some like this zero polynomial identity testing. I explain some aspects of it.
Okay.
I explain determinant versus permanent and so on. Some things I explain.
Okay, fine. Sure. Okay.
But if you're interested, I could share. You can ask a question. I could share some material, like some.
Sure.
There are. I think there may be some lecture material notes or something that are there online. I could find and share it.
Sure, sir. I'm actually interested in algebra, so like.
Sure. Your next question was, can you do computation analysis over FA model? So by FA, I suppose you mean finite automata?
Yes, exactly.
Finite automata is a much weaker model, right? So if you have done a TOC course, theory of computation course, the what you can compute over finite automata are much lesser than what you can, like it's much lesser than like the class of decidable problems. Like
0 power n, 1 power n is not decidable by FA.
yes, so that's not a regular language, right? So it's a very limited model, whereas Turing machines are something that is equivalent to it's something that are equivalent to like any kind of the at least conceptually equivalent to the modern day computers. So that is why one reason why we study Turing machines over finite automata. Right.
Okay, but I like. Well, strictly speaking, like we will be able to define all this P and P stuff in the finite automata thing also.
No, we
right?
cannot, because finite automata see the kind of things that you can do are very limited, right? So basically, it's like think of a Turing machine with a finite tape, finitely long, like maybe limited amount of tape. This is what you can do with an automaton, finite automata. So there is a limit to what it can compute. So yeah, I don't think you can define P versus NP in that setting.
Okay.
Yeah.
Okay.
Yeah.
Thank you, sir.
Yeah, sure. Then I think what's the next question? Vivek with Himanshu. So Abhay is there who has not asked anything. And there's Atul who has asked its importance and how to start learning. I don't think Atul is present here, but the question is also vague. Its importance and how to start learning. It's a very vague statement, so I don't know what to say for that. So I'll skip that also because Atul is not here. And the next question is from Goel. 3 questions. Please explain polynomial hierarchy, purpose, and its meaning of its collapse. In other resources, it's also explained using oracles. PH is a bit difficult to comprehend. Okay. So, and then there are, okay, the other thing, is it possible to conduct sessions specific to writing a small conference level paper for those participants who are keen to make it TOC complexity a potential research area and unaware of the starting point problems, since theoretical computer science is not a common area of research contrary to data science ML? Rest, Mr. Bhargav is doing an excellent job of clarifying the course content. So I'm happy to note that Bhargav, you're enjoying his sessions. I'll come the reverse order. Specific sessions. So what you're requesting is not really within the scope of this course, because the scope of this course is an introductory course to this entire area. You are asking how to get into research, etc. While we could, like in some sense, it's like what Vivek asked. So it is not something that I could host 1 session or 2 sessions. It may require some something that is beyond hosting a session or 2. It will require some conference or something like that, some event or a workshop where we actually have participants and
Or sir, probably, yeah. Good evening, sir. So, or probably, sir, it could be a summer school kind of the thing.
So that I will consider. Like, I'm glad to note that there are people who are enthusiastic about this. So it is not a common area, contrary to data science ML. That is correct. But then it can, like, the common area, not common area, is because how many people choose it, right? So if more
Yes.
people and more people are interested, it will become a common area, and I hope it does become a common area. And if you have more people, then of course there will be more research activity, and of course the science will grow as well. But this is something that has to be done outside the scope of this course. We should, if you remind me sometime, or next year or something, I could consider like a summer school or something like
Yeah,
that.
sure, sir. And sir, if
But
possible,
there may be, like, there are conferences. There are two conferences that I can think of. Like there are some conferences that like FSCTCS that happens every year once. Usually associated with that. So this happens in India, FSCTCS, where people talk about various aspects of theoretical computer science, also complexity theory. It usually has some affiliated workshops, so you can just so this is something that you can check out. So this is the name of the conference, FSCTCS. I think the name expands to Foundations of Software Technologies and Theoretical Computer Science.
okay.
But every year this happens in December. I think this year it's happening in IIT Madras, but next year I don't know where it's happening. It happens in December anyway. So this is one opportunity, is to attend these conferences. It happens in India, so anyway, it's not like traveling internationally.
So, sir, is this possible that you share a small conference paper which could work as a starting point to start working in this area? Like, say, I started searching few papers, and fortunately or unfortunately, I ended up with that journal, theoryofcomputing.org. And even the titles of the papers were not, I mean, were beyond my reach. I was not able to understand what's the meaning of the title of those papers. So a small conference paper which you think that after having understanding of the topics which you deliver, we can start with.
I can think of, but it's a very open-ended question, because sometimes even the complexity of the titles may not be really, it may be very minor starting block, because perhaps it's just like if you read the paper, maybe the first 2-3 definitions, the title is explained. Maybe it's just the name of a problem that they're taking. So if I tell you subset sum, perhaps somebody who's not taking this course may not understand what it is. But then it's a very simple problem, right? Given a set and a sum, you're asking if there's a subset that adds up to this sum, right? So but then if you have it like title which consists of such terminology, sometimes that is itself putting off people.
Yes.
But what I'm saying is the difficulty of the title itself may not be an indication. But let me see. Let me see. I will, if I don't share, like, you please send me an email.
Sure,
I'll try to find some paper that could be easy to.
Sure, sir. Sure. Thank you, sir.
Yeah. Now, finally, the first question that you have asked is, please explain polynomial hierarchy, its purpose, and the meaning of its collapse. In other resources, it's explained using oracles. Even I explain using oracles, but later in the course.
Yes, I saw it in the 4th week, sir.
In the 4th week.
Yes.
So it's basically the idea is using just like NP is like we have an existential quantifier.
Yes.
So now the question is, if you have multiple quantifiers, what can you accomplish? And so that is the question that naturally leads to the definition of these classes in the polynomial hierarchy. So existential and universal quantifiers. And then you define classes such as sigma 2, pi 2, and so on.
Yes.
Right. So collapse means that as of now, so maybe I'll just present. Just hold on. I'm just trying to present the screen. So let me know if it is visible.
Visible.
Okay. So P is this. A language is in P if you can decide it using a deterministic polynomial time machine. And NP is like you can verify it provided you are given a certificate. So X is in the language. This can be verified with the help of a proof or witness or certificate string, which is Y. And similarly, co-NP, right? So now the question is, can you combine or can you have both? Can you have this combine? Can you combine this existential and universal quantifiers? So let me just one second.
And sir, where is the need to combine these quantifiers, that two alternatively? What's the need? I mean,
No, so what is the need to combine? So you are just interested in knowing what is the computational power of this. That is why you combine this. And what is the need to combine it alternately? Because if you have two existential quantifiers coming one after the other, there exists, then you may as well combine it into one quantifier, right? There is no need to, like if it is there exists Y, there exists Z, then instead of considering them as two strings, we are just looking at one long string that is Y followed by Z.
Right.
But then that means it's just a bigger certificate or bigger witness. That is not really adding any further power. What we have understood so far is that by combining them alternately, only then do we get more power.
Yes.
And what we know so far is that this sigma 2 contains NP as well as co-NP. Right, sigma 2 contains NP as well as co-NP. Pi 2 contains, pi 2 also contains NP and co-NP. And if you have three quantifiers, sigma 3 and pi 3, the sigma 3 contains pi 2 and sigma 2 and so on. So you end up with this kind of a picture, which I may have in the notes. Yeah, this is a kind of representative picture. I think I've scrolled past it. Where we have this hierarchy kind of structure. And this is okay. Here it is. So P is contained in NP. P is contained in co-NP. NP and co-NP are both contained in sigma 2. They are both contained in pi 2 while they are not comparable. And all of this is contained in sigma 3 and pi 3. Right? Like that, you can keep drawing this or keep having these hierarchies. And we know some things like if NP is equal to co-NP, then we know that sigma 2 and pi 2 will also be equal to NP and co-NP. This is covered in the course. And if at any level, let's say sigma 3 equal to pi 3, then basically sigma 4 also will be equal to sigma 3. Sigma 5 also will be equal to sigma 3. So if at any point these two are equal, sigma I equal to pi I, then everything above will also be equal to that level. Right? So, so this is called a collapse, meaning as of now, we don't know whether all of this could be sigma 1, sigma 2, sigma 3, sigma 4. All of them are separate. We don't know if they're all separate or not. But when we say, let's say, if you show that P is equal to NP, then everything collapses to P. Suppose we show that NP equal to co-NP, then everything is equal to NP, which is also equal to co-NP. Suppose we show sigma 1 equal to sigma 2, that also means that everything collapses to sigma 1, or sigma 1 meaning NP. So if you show that at any I, sigma I equal to pi I, or sigma I equal to sigma I plus 1, then everything above will collapse to sigma I. Collapse meaning everything above will be equal to sigma I, which means a hierarchy like I have drawn in this picture will not exist as it is. Instead, if all the above levels will just be at that level. Like which means by adding more quantifiers is not really adding any further, it's not really giving any further power. So in another way, the P versus NP question is this, right? So if we have a verifier, so is verification the same as deciding, right?
Yes.
Given X, you are able to decide whether X is in the language, or given X, with the certificate, you are able to verify that exists in the language.
Yes.
So now basically you're asking whether the existence of a certificate is needed or not. This is the P versus NP question. So now similarly, this sigma 1 versus sigma 2 or sigma 2 versus sigma 3 is also similar such questions, right? So we are trying to understand whether at a higher level is this necessary or not. This is the polynomial hierarchy. Yeah, and this is what I explained is what it means.
Yes, sir, I understood this thing. And sir, at few places it was written that sigma 2 is equal to NP raised to the power NP kind of a thing, wherein say NP is given and then NP as the oracle stuff. And in this way, they used to draw this figure which we have drawn here. And in the textbooks, they used to draw in some other formats. So probably through oracles or by some other means. So then it becomes.
I'm not getting what figure you are referring to and what other format.
Not in your lecture notes, sir, but if I Google this polynomial hierarchy, then I find that figure wherein they have P, NP, and then NP raised to the power NP. And
no,
then
I think that is just NP raised to the power NP is just sigma 2. That is a sigma 2.
Yes. Okay.
So this is covered in the fourth week, as you pointed out. I think lecture 24 is where I cover it.
Okay, sir.
I think if I understand you correctly, you are just saying that there is this figure is the same, but the labels are different. Is that correct?
Yes, sir. Yes.
So basically now you can represent, that is the oracle, the NP raised to the power NP is just the oracle representation. So by that, it means that NP with an NP oracle, right? So which means that is what NP to the power NP means.
Yes.
So it is like the, I think Turing reduction, NP to the power NP. Now that is, you can show, I think I show it in the lecture notes as well. NP to the power NP is, NP to the power NP is equal to sigma 2. Yeah, Turing reduction. I think this is chapter, this is the 24th lecture or 23rd and 24th lecture. So then I show that sigma 2 is equal to NP to the SAT. So NP to the SAT is the same as NP to the NP because SAT is as good as any other NP language.
Right. Yeah. Clear, sir. Thank you, sir.
Okay.
Any other questions? Yes.
Sir, I have a question over here. For example, this definition of convergence of the sequence. So there the definition is for every epsilon there exists a n. So does such kind of problems also fall in sigma 2?
No, that is a definition, right? So there is no deciding problem, right? What you're talking about is definition of continuity, right? For every epsilon, there is a delta. Is that what you're saying?
Yeah, a definition of convergence of a sequence.
So it is like for every epsilon, there should be an n such that beyond that n, any two terms or there should be a limit and all that. Like
yes, sir. Yes, sir.
So limit. Let's say there is an excessive limit if x minus like x minus xn is always less than delta or something like that, like beyond a point.
Yes, sir. Yes.
But that is a statement, right? Here we are saying there should be a machine that decides. So I don't think so there is no machine or there is no deciding or there's no algorithm there.
So for example, if someone gives us the value of n, maybe we can easily verify after that the distance is within epsilon or not.
Okay, so when you put it that way, yes. So that's like saying that for all yeah. So then you are trying to phrase it like a sigma 2 problem.
Exactly, sir. Yeah.
Sigma 2 or pi 2. So for all epsilon, there exists an n such that it's more like a pi 2 statement.
Yes, sir. Sorry, sir. Pi 2.
Yeah. Yeah. Any other questions?
Sir, I have one question.
Sure.
Like you were during the lectures, you were talking about sublinear space, and we mentioned only log, right?
Correct.
Okay. So there could be other sublinear, right? Like for example, like some n power 0 point something,
So
right?
square root n or something. Yes.
Yeah. Okay. Like how does one construct such languages? Like sublinear in say order of n power 1 minus epsilon for some epsilon.
Some of these are found in streaming, for instance. So anyway, login, you have examples like palindrome and all is login.
Yes.
But there are examples in streaming where one occasionally deals with huge input data, and you want to process in much smaller. You cannot afford to devote so much space. So this is something that is there in like one area I can think of is streaming, where as a result of like you can show that some problems like for instance if the input is huge and you want to, let's say, input comes from let's say there are like 10 types of objects, 1 2 3 4 5 6 7 8 9 10. You want to count how many of item 1 appeared, right?
Right.
So you have a stream of data, you have 10 types of possible objects coming.
Okay.
You want to count like some statistics of these things coming, the stream coming. So in such cases, I think we have algorithms where we have this sublinear. There is a requirement for sublinear space simply because the input data is huge. And there are such algorithms, and usually what happens is these algorithms itself are not, they're like randomized algorithms, and that there is probability of error, etc.
Oh, okay.
You'll end up getting and giving approximate statistic than the actual statistics, because but then you will do it efficiently, space efficiently.
Okay.
So that is one area where I can think of right on top of my head, where square root and or such n power point something, that such kind of space utilization is there.
Okay. Same thing for like subquadratic in time complexity. So that means like
Subquadratic, we may already see such things. Right? You may have already seen such examples in subquadratic means n power n. So for instance, sorting itself is subquadratic, like n log n, right?
Okay.
A subquadratic time is not really that surprising. We know algorithms that run in 2.5 n power 2.5 running time. There are matrix multiplication that runs in something n power some exponent, that where the exponent is between 2 and 3, right? You know Strassen's algorithm, which is like n power log 7 to the base 2. This is a number between 3 and 2.
Okay.
Like this comes out as a result of this master theorem, this recurrence relation, how it is solved, etc.
Okay. Sir, actually, I don't have much background in this computer science. Like I am a mathematics student. I'm just taking this course out of
So
curiosity.
my suggestion then would be to go try to read up on like master theorem, recurrence relation, master's theorem and recurrence relations. Just try to read up on this. So basically, this is there is this algorithmic technique called divide and conquer.
Yeah.
Where what you do is you have a problem and you split it into smaller sizes of the problem. You solve the problem in the smaller sizes and then combine them. And what happens? So you need to spend some time in splitting it and combining it, and you also need to spend some time in solving the smaller instances. So then you end up getting what these recurrence relations, so the running time of the bigger problem will be can be expressed as the running time of the smaller problem. So for instance, you get relations like this: t of n is equal to 2t of n by 2 plus n square, or something like this.
Right.
And then when you solve, so these are called recurrence relations. The time complexity for solving a problem of size n is equal to 2 times the time complexity of solving the problem of size n by 2 plus some n squared, or something like that. And then master theorem is a theorem that is used to like solve such recurrences. So you can try to solve these expressions. So then you will get, there are some formulas like that. So I suggest that you read up these things. So then you will see a lot of examples of like algorithms that run in n power k time, where k is not an integer, right? The k is something like between 1 and 2, between 2 and 3, and so on.
Okay.
Yeah.
Sure.
This is like if you look up basic algorithms textbook, like second year algorithms textbook, second year basic algorithm, you'll find this. Like
yes, sir. I think I've seen it, but I've not
so
worked
CLRS
with it.
is one example.
Yes. Okay.
And, there is also this Das Gupta Papadimitriou Vazirani. That is another good book for algorithms.
Right. Okay.
Okay.
Sir, I have one more question. I'm not very clear about the relationship between the path and the non-deterministic machine. So for example, how to show about that path is in NL.
Okay.
So how to convert that path, how to see that path as a non-deterministic machine?
Okay, so that, let me just share my screen again. The reason is basically every NL machine, every space, every machine with limited space, you know the configurations are bounded because you know that the space is bounded. And then it is about searching, and also you can always also convert any machine to a fixed starting and fixed accepting state. Then if you are asking is X in the language, or is X accepted by this machine, you are asking, is there a way for this string or this graph, this configuration graph, does it have a path from the starting state to the accepting state, or starting configuration to the accepting configuration? In the case of a deterministic machine, like it's just like one configuration after the other. In the case of a non-deterministic machine, there could be multiple, like if you see the screen now, there could be multiple successors to the starting state, starting configuration, and multiple successors to each of the successors configurations, and so on. So now the question is, can we somehow reach from here to there? So now if you look at this graph, it's like you're asking, is there a way to start here and end here? Or in other words, is there a path from here to here? So this is why, so this is the case for any non-deterministic space-bounded machine. This is true for any non-deterministic space-bounded machine. So that is why now you're like the path problem is equivalent to asking whether a non-deterministic space-bounded machine, when given the input X, leads to acceptance. Right?
Yes, sir.
So
yes.
This is the basic idea. This is the basic idea, yeah.
And sir, in your lectures, you explain that how to map multiple accept states to a unique accept state,
Right.
and the head can go back and erase.
A configuration, not state.
Yeah, yes, sir. Configuration, and the Turing machine head can go back and erase the
Correct.
symbols. But actually, I didn't understand the meaning. What exactly?
So what's the configuration? Can you tell me what's the configuration?
Yes, sir. The configuration consists of the tape contents, the head location, and the state. And the state.
So accepting statement, you're already at the accepting state, right? So now, but you may accept when the head is somewhere, the tape content may be somewhere, but I don't. So what if? So if I accept the head, so that could mean there are several accepting configurations. So now I will make a new accepting state. So instead of accepting, what I will do is, when I go to the accepting state, I will start erasing everything that is there in the tape. Okay, and then I will bring the head back to the leftmost location. So this way, what I'm doing is I'm removing. So how can a accepting configuration change? Like how can there be multiple accepting configurations? There is only one accepting state. There are multiple accepting configurations because the tape contents are different and the head position is different, right?
Yes, sir.
So now you want to remove the variability there. So which means you want to change the variability of the tape contents by erasing the tape content. So now that the tape content is empty, you want to remove the variability in the head position by bringing the head to a standard location. So which we say the standard location is, let's say, the leftmost location.
Yes.
So so once you insist on these two upon acceptance, now the only difference is there's no difference. Whenever you are accepting, you have to erase the entire tape, which means there is no variability in the tape content. You have to bring the tape head back to the leftmost. Hello? Hello?
Yes, sir.
So sorry, I think my home, there was an internet issue. So now I'm joining from the hotspot, so which is why I've disabled the video.
Yes, sir.
So what I'm saying is the variability is there in the tape content and the head position. You're removing that by insisting that you come back to the leftmost position and erasing the tape head. Anyway, there is only one accepting state. So that state remains the same. So now everything becomes standardized. When you accept, the tape contents are empty, the head position is leftmost, and you are at the accepting state. So this way you can convert. Like if a machine has multiple accepting configurations, there will only be a unique accepting configuration.
Yes, sir. I got it. Thank you, sir.
Yeah.
Yes, sir.
Any other questions? If there are no other questions, I think we could wind up. So thank you for I think all of you who turned up: Goel, Vivek, Himanshu, Rakshit, and Harit. Maybe hope you keep your interest in the course and actively participate in the course. Keep participating, keep asking questions, and yeah.
Thank you so very much, sir. Thank you so much.
Yeah.
Thank you, sir.
Thank you. Bye.
Bye, sir.
Bye.